we'll get started. Yeah, again, thanks everybody for coming. I looked at the attendance list ahead of today's science session. I was so pleased to see so many friends and colleagues on the list. There's a lot of interest in this topic. I think many of us talk about PFAS at a rate and a frequency with which we would have never expected 2 or 3 years ago. It certainly is a topic that's right at the forefront of our industry, and we have a really interesting presentation today talking about one approach to managing PFAS sequestration in disposal facilities and other environments. My name's Craig Benson. I'll be your moderator today, but I won't be doing most of the speaking. Our speaker is Todd DeJournett from Geosyntec Consultants in the Twin Cities area in Minneapolis, Minnesota. Todd, could you push ahead to the next slide? We're using one presentation, so Todd's going to be driving the slides while I talk. I just want to take a few minutes to talk about EREF for some of you who may not be familiar with the organization. I've been involved with EREF for about a decade in a very intimate way, serving on the Research Council and being involved in a variety of different activities. EREF is an organization that was created to promote sustainable solid waste management and to drive us towards a circular economy. It has a variety of different components. It has research grants. That's a research council that, for example, that I serve on, that's providing grants to academics and others to conduct applied and translational research to solve interesting and challenging problems in sustainable solid waste management. An education program developing curricular materials and different types of educational materials to provide greater opportunities for learning in solid waste management. A scholarship program, which is just wonderful for master's and PhD students to get support for their graduate education. And then finally, a data and policy program, which writes reports and other specific topics based on an analysis of data and other types of research to write policy statements and documents to help guide the industry. EREF really has evolved into a very powerful and helpful organization for our industry. Can you get the next slide, Todd? The science sessions, I don't know how many of you have attended some of these before. I have enjoyed them thoroughly, and I enjoyed them so much I volunteered to be a moderator. We'll be about an hour long. We'll have about 45 minutes of content, but and about 15 minutes of Q&A at the end. But I also want to make it clear that if you've got questions in the middle, we can jump in. All right, we want to make this more of a discussion and sharing experience than a lecture. The science sessions are on a variety of different topics, but it's all about kind of current information that's coming out. And certainly what Todd's going to talk about today is right at the leading edge of technologies to sequester PFAS. We'd like to have lots of interaction. As I indicated, Todd's not here to give us a lecture. He's here to talk with us. We want to have a conversation. And equally important for all those who are participating, we offer PDH credits as an outcome of participating in the session. So some of you who are, for example, I'm a professional engineer and I need to collect a certain number of PDH credits each year to keep my license. This is one way that we can provide that type of assistance to you for participating. Todd, can I get the next slide? While we haven't been diving in yet to today's presentation, we want to have an advertisement for next week's as well. So today we're going to talk about PFAS sequestration. Next week, Mike Wong from Rice University is going to be with us to talk about how to accidentally destroy a forever compound, talking about destruction of PFAS compounds. So today we're talking about sequestration. Next week we'll be talking about destruction. So please join us next Thursday. If you haven't signed up already, please do that afterwards today. I think you'll enjoy both of these a great deal. Next slide, Tom. Our presentation today wouldn't be complete without a thank you to those who make it happen. These are the sponsors for today's session. EREF is a nonprofit organization. Its success and the things that it delivers are highly dependent on those organizations, individuals, and companies who support EREF. Thank you very much for these sponsors for making this happen today. And one more slide, I think I got there, Todd. Some housekeeping. Everybody stay muted. I don't know if you even have the ability to unmute, but we'll make sure that the audience is muted just so there's no interference in the background. We have a questions box in the GoToWebinar control panel. Please submit your questions through the questions box, not through chat. Submit it through the questions box. And I will then look through those, keep an eye on that, and pop those in as needed during the discussion or afterwards. If you have a question or have a concern about some of the technology, chat with the organizer. You'll see that in the chat section. We'll be able to get you help if you're having some difficulties. The slides that we're sharing today will be available for download. All right, so check the handout section in the GoToWebinar control panel. And actually, I see it right now. I just took a peek there to make sure they're there. They're in PDF. Feel free to download those. And then you'll get your certificate of completion by email on Monday. So look for that coming down the road. Next slide, Todd. And enough of me talking. I'm going to turn it over to Todd. Todd, as I indicated, is with Geosyntec in the Twin Cities area. He's an environmental engineer with a wealth of experience working with industry on a lot of practical but complex problems. And he's bringing this expertise and his collaboration with others at the University of Minnesota through the MinDrive program to really challenge this difficult problem of PFAS. I wanted to just say one thing before we leave, and I turn it over to Todd. These types of programs that Todd's involved with, industry academic partnerships to solve difficult practical problems for our society more broadly, are where the action really is. They create tremendous outcomes that help us solve these really challenging problems. And I want to commend Todd and his colleagues for getting involved in that type of collaboration. It takes commitment and it takes sharing of different ways of going about business, but this really creates outcomes. And I just wanted to mention how important I believe that is. So I'm going to turn it over to Todd now.
Thanks very much, Craig, and thanks everyone for joining today and giving me this opportunity to tell you about our project that we're doing with the University of Minnesota and EREF. Title of the presentation is Storage Wars, which, as the title suggests, we're trying to sequester PFAS, that's per and polyfluorinated alkyl substances, using polymers to remove them from leachate and put them back in the landfill, where hopefully they will stay put. The title is particularly fitting, I think. If anyone's ever seen the television show Storage Wars, you know that this is a program where folks bid on these storage lockers that are full of various items, and in the hopes that they find a Van Gogh painting or maybe the Ark of the Covenant or something inside there. But if you watch the show, you know it never really happens. Much like that here, you know, we are trying to search for a good solution to PFAS, but it's a difficult challenge. And of course, as you'll see, we don't have the silver bullet, but we have learned a lot in the process of seeking that. So, you know, with that, we'll get into the presentation. I also want to say too, you know, I'm hoping for an interactive discussion as well. And so, Craig, certainly as questions pop up, you know, feel free to jump in and interrupt me at any time to start a discussion about anything that I'm talking about, or even a different tangentially related item. So this is just an overview of what I'll talk about in the discussion here. First, the who did the work. I'll tell about our research team. Then why did we do it? What's the value proposition? What are we trying to accomplish? the concept, what are we trying to do, and then the technical challenges, what could go wrong. Then we'll talk about how it worked, the results that we've got to date, and then also the next steps. What are we going to do next going forward? So first with the who, this is a collaboration, as Craig mentioned, under an EREF project for treating PFAS and landfill leachate, a collaboration with Geosyntec consultants and the University of Minnesota. From Geosyntec consultants, there's myself, James Wang, and Jeremy Morris, two engineers from our Columbia, Maryland office who are collaborating with me on this. And from the University of Minnesota, we have Matt Simsick, who's in the Department of Public Health there, and Bill Arnold in the Department of Environmental and Civil Engineering. Bill is actually my old PhD advisor. Well, he's not old, but he's my PhD advisor from many years ago. And it's really been fantastic to get the chance to work with him again all these years later on something important and different. Craig mentioned the MnDrive program, and they're actually partnering in this as well, co-funded by EREF and MnDrive for this project. And it's actually a really excellent match between the two, where we get some synergy in terms of not just the funding, but then also the objectives. MnDrive is an industry outreach program through the University of Minnesota that is aimed at increasing collaboration between university faculty and industry to work on environmental problems that are important to Minnesota industry. And certainly PFAS and landfill leachate is a very important problem to Minnesota industry. And so it's a really excellent match. So why are we doing this? PFAS, as most of the folks on the call likely know, is a very widespread issue across the globe. PFAS and landfill leachate is also a very hot topic, although I think the science is still developing in terms of what all the sources of PFAS really are, and whether or not landfill leachate factors in as heavily as some folks once thought. But nonetheless, it has received a lot of study and interest in recent years. In fact, the topic is so broad, you have to put some battery limits on it in order to even get your arms around it. And so from our perspective, as well as the focus of MnDrive, we're really looking at PFAS and landfill leachate in Minnesota. And in that particular topic, the Minnesota Pollution Control Agency has been collecting a fair amount of data over the years regarding the concentrations of PFAS compounds in the landfills that are in their closed landfill program. And this figure here, the map of the state, is just a summary of their findings to date on that. And as you can see, they're highlighting areas where PFAS was detected, where PFAS exceeded the Minnesota Department of health-based values in the leachate, and where it was much higher, or 10 times or more higher than the health-based value. I've included in the table to the right here a summary of the Minnesota Department of health-based values for PFAS compounds. There's a handful of them, more than there used to be. And even since we began this project, some of these values have been ratcheted down as well. So not only is it a challenging problem to begin with, but you also are chasing a falling standard as well. And then as if this isn't enough, you can take this times 50 states, and there's a whole patchwork of other requirements that really make it challenging to really get your head around the problem, let alone the solution. One of the points I want to make from this this map is if you look at the distribution, you might come away with the conclusion that, well, this is a metropolitan area issue, or it's more prevalent in the metropolitan area, or more of a problem there. Certainly, there's a number of observations in the metro area, but really you have to think in terms of the scale relative to the operation as well. Some of the operations in outstate Minnesota, they also face a significant challenge, even if their concentration aren't as high, just because of the nature of their operation. There are a number of landfills in Minnesota that still spray, irrigate, or dispose by spray field of their leachate. And for those operations in particular, the PFAS issue is really looming as a potential future problem. They're receiving more scrutiny from the regulators. And now, in order to open a new spray field, you actually need to demonstrate that your leachate concentration is 1/4 of the MDH health-based value. And so that results in some numbers that are really quite low for some of these, and a real challenge for operations in outstate Minnesota, where putting in, whether you're talking about trucking to a wastewater treatment plant that's large enough to manage that waste, or if you're talking about some type of advanced treatment process on site, all of that translates into higher tipping fees, higher costs. And these operators all know that when those costs go up, they start seeing more hillside dumps, more burn barrels, things of that nature, that really, gives you a good perspective when you talk to these folks about the sustainability of trying to manage this leachate. And in fact, the genesis of this project to begin with was we were approached by an operator in outstate Minnesota who was facing this very situation. And they said, can you help us come up with something that is practical, implementable in our situation? And that's where we immediately took this to the University of Minnesota. This was even before engaging with EREF, and started talking with the faculty there to see what they were working on, what could we do. And sure enough, found out that Dr. Simsick and Dr. Arnold there had been working on this particular approach using the commercially available cationic polymers to increase the sequestration or the retardation of PFAS compounds in groundwater aquifers. And so that really, matched sort of what the challenge was, which is to come up with something simple and implementable. The question then, of course, is, well, how would we do this in leachate? Would it work? How could we deploy this in a way that maybe would make sense?
Hey, Todd.
Yes.
We had a question from Tess Brester. First, with the sampling that was done at these sites you show on this map, were they voluntary sampling and testing, or was this mandated by the state? So, for example, some states are actually requiring sampling and testing throughout the state. And then a follow-on she had is, does Minnesota have labs that are certified to sample and conduct analysis for PFAS, or are those samples going out of state?
Oh, good question. So I believe, I don't know the exact answer to both of those questions, but I can try to get close. As I understand it, in terms of the data collected here, this was collected from closed landfills that are being managed by the Minnesota Pollution Control Agency. So voluntary in that, I suppose the Pollution Control Agency, can collect samples from the landfills they're managing whenever they like. So I guess voluntary in that regard. With respect to PFAS analysis, I do believe that PACE, I don't know if the PACE Analytical Lab here in the Twin Cities, they may be certified for PFAS analysis. Other than that, I know that a lot of the Department of Health PFAS analysis has been conducted actually in the SIMSIC laboratory, at least a lot of the early work that was done. But I think too, because of the volume, a lot of it, regardless, does end up going out of state just because of capacity. We have a lot going on, as some may know, in Minnesota related to PFAS sampling that extends really far beyond landfill leachate and the scope of this particular project.
One other comment that came in too, Todd, from Richard Hampel. He was wondering if you could comment just about the persistence of these compounds in disposal versus, for example, in the landfill versus as opposed to once they're spray applied on a field. Are either of those environments more likely to degrade those compounds or not?
I don't know that there's in terms of degradation, I don't know that there's a lot of difference between the two. Some of these shorter chain compounds, I know that, and we'll see in some of the data, they're more mobile. So the thin spreading may, encourage them, leaching out more potentially. There has been some data, or they're starting to look at some data for volatilization of some of these shorter chain compounds. I don't know if that could be a major loss mechanism in a land application or thin spreading operation, but I know there's some data that's starting to be generated about the vapor phase of these.
Thanks.
Good questions. Thank you. So in terms of the idea that we developed with the university, the initial idea was applying this to treat the leachate as it's generated from the landfill using a solids contact process as shown here. So here we're using solids that are innate to the leachate itself, settling those, taking a portion of that, amending with polymer to improve its capacity to sequester and absorb the PFAS, contacting it with the leachate, and then settling out again. And then as in terms of the final disposition of those solid materials, taking them, putting them back into the landfill, where hopefully the PFAS remains with the solids. Then the effluent from that process then, in the case of spray fields, if we can knock the PFAS down enough to get below that 1/4 number, the hope is that that could then be give the operator the flexibility to continue to do land application of that PFAS compound of the landfill leachate. So there really, with this, are two research questions to be answered. One is, can we get the PFAS to stick to the solids in the first place and get them removed from the leachate? And then the second question is, if we can get that to occur, can we get the PFAS to stay with the solids once it's placed in the landfill? So there's a removal efficiency question and then a leachability question related to this approach. Another idea that we thought about, and this one is, we're giving a more thought to this as we proceed with our research, is incorporating the polymer into daily cover. So here you're effectively doping the daily cover materials with the polymer to try to improve PFAS retention within the landfill itself, keeping the PFAS out of the leachate collection system, trying to keep it within the footprint of the landfill, which has some benefits from a risk management standpoint. Some other possible benefits of this approach include lower concentrations of other constituents in the leachate if it hasn't percolated through the entirety of the waste material. And then also, and this was one thing that I thought about, with the daily cover being both above and below the waste, besides the daily cover helping to control odors, if we have doped it with the polymer, perhaps it can cut down on any volatilization of PFAS compounds from the waste, if that turns out to be an issue. I don't know if that's something that some data is being generated on now. I don't know if it's sort of emerged as a major issue or not, but that could be one benefit of this approach as well. So what could go wrong with this approach? What are the technical challenges? We talked about matrix issues, the fact that this was applied previously in groundwater. Leachate is much different than groundwater. It has higher total organic carbon content and a higher ionic strength than groundwater. Both of those things could interfere with the binding of the PFAS by the polymer. Also, variability in pH could affect performance as well. Particularly with the leachate treatment embodiment of the idea, there are some implementation issues to consider. Limited space available generally at landfills where the leachate is being managed, and limited infrastructure to pump things to and fro, add things here and there, separate solids. All those are limitations of trying to do something in the leachate management system. We discovered a number of analytical issues with respect to PFAS in landfill leachate. The initial method in the SimSiC lab using the GCM-SMS, we were doing direct injection, which we found it worked well for detecting the PFAS, but after some amount of time, it kind of wrecked the instrument. It's fixed now, so that's good. But we did find that we had to switch the method to a solid phase extraction process, which still gives us good detection of the PFAS compounds, but is a little easier on the instrument, or at least we hope so. So what did we find? This is a summary.
Hey, Todd, let me ask you a couple of questions before we jump.
Yeah, go ahead.
I was on mute. I apologize.
Oh, it's all right.
Couple things came up. I think you answered one. Eugene Radcliffe asked about what analytical methods, and you said GCM-SMS, right?
Correct. Quadrupole GCM-SMS. Yes.
And then the question from Brian Brazil was really going back to an earlier slide, but thinking about the solids that you'll create from the polymerization process, where you're binding the PFAS to the polymer. Do you expect to dewater that it must be like a polymer hydrogel that forms, or to stabilize that before you put it back in the landfill?
Yeah, the dewater, so filter press or thickener, really trying to manage this much like a waste sludge from a water treatment process, really, is how we envisioned it. So yeah, it would be dewatered to some degree, get the free liquid out of it before placing back in the landfill.
Yeah, thanks.
Great. All right, so leachate characteristics. So we tested 3 different sources of leachate, and so I have some general characteristics of those samples here. We had 2 sources that are relatively low strength, low COD, but somewhat higher ammonia nitrogen concentration. And we had source 2 here, which is relatively high COD, a little bit lower ammonia, but a higher total PFAS concentration. In terms of the compounds we analyzed that make up that total PFAS, we analyzed 24 different PFAS compounds with Dr. Simcik's instrument. That number of compounds is somewhat unmanageable to really present and discuss. So what I've included here is a subset of that, particularly for a broader audience. I wanted to look at those compounds for which there were published ranges of concentrations in landfill leachate, so that we could just kind of get a gauge on how these samples compare with others. And so by and large, as you can see from the figure here, fairly similar to what's been reported for other sources, with a few exceptions. PFBA in these samples appeared to be a little bit higher than what's observed elsewhere. And I did include as a cheat sheet here the table from earlier with the health-based values. And so, you know, the PFBA here, you can see we do have a health-based value. It's relatively high here, but you know, again, maybe reflecting the fact that we have relatively more PFBA here than what's been reported elsewhere. We have one sample here at relatively high hex concentrations. Yeah, this particular sample was high. I think we had some others that fell a little more closer to the normal range. But overall, in terms of prevalence of the different PFAS compounds, the hex was the most prevalent observed in the samples. Also here, relatively low PFOS concentrations and relatively higher PFOA. We'll get into that in a little bit more detail later, but perhaps reflecting a little bit more mobility of the PFOA relative to the PFOS, a difference between the functional groups there. So the first thing that we did, because we're trying to increase the partitioning of PFAS onto the solids. So the first thing we did was to try to look at what we were starting with from the standpoint of partitioning just in the ambient solids that were collected with the leachate. This is basically, this upper table is a sample, the total matrix, get the total PFAS concentrations, centrifuge to knock the solids out, sample it again, and then look at the difference and infer, okay, how much solids did I have? What is the distribution coefficient for the PFAS compounds on those solids? And so that gave us the numbers here for the three different sources. And again, you know, one thing to point out here is the PFOS versus PFOA. At least in a couple of these, we see that the PFOS has a tendency to partition more to the solids than the PFOA does, which I think is relatively consistent with what you know, is generally observed for the behavior of those two compounds. In looking at the previous work that was done, and again, this was done in groundwater with aquifer solids. The first thing that we can look at is a comparison of the distribution coefficients for these compounds in the aquifer solids as compared to the solids in the leachate up here. And what we can see is that in general, the solids that are in the leachate have a greater capacity, or there's greater partitioning of the PFAS compounds onto those solids than there is for these aquifer solids, which again, I think makes sense given that the leachate solids are more complex, have more organic matter in them, more stuff that has the potential to coordinate or bind with the PFAS compounds. The other piece to look at here, we're working with polydadmac is one of the polymers, and the other polymer is a polyamine. And again, these are high molecular weight polymers, commercially available, nothing special or fancy about them, routinely used in water and wastewater treatment. Here, when applied to the aquifer solid, you can see the effect on the distribution coefficient. It increases the partitioning of the PFAS onto the solids. So this is what we were hoping to accomplish in the leachate. One thing to point out here, and this is, this was another thing we thought was promising, is that the effect on the PFOA in particular was pretty significant. And given the PFOA in our leachate samples was relatively high, we thought that could be a good potential for improvement here through the application of the polymer. So how did we do? This is one example. We ran a number of tests applying the polymers to the leachate and looking at the effect on the aqueous concentrations of PFAS in leachate after treatment. And this is again for the same subset of compounds that we had before. What we can see is not a lot of change when we add either the polydabmac or the polyamine. Perhaps we see a little bit of effect of the polyamine here on the PFOA, which again, perhaps that's reflective of the fact that the PFOA is particularly more influenced by the polymer than the other PFAS compounds are. But again, not a lot of removal. We tried this at polymer doses ranging anywhere from 50 milligrams per liter to 1,000. We didn't see a whole lot of benefit of adding higher concentration or higher doses of polymer to the leachate in terms of the amount that partitioned onto the solids. Similar story in source 2, although perhaps even less effective here. Again, this is the stronger leachate in terms of the COD concentration. Not a lot of difference, or tough to discern any difference at least between the different treatments. Perhaps we got a little bit of removal of hex here, but pretty minor. And again, a similar story in source 3. This is again the other less concentrated source of leachate. Very similar to the other two, not a lot of removal. We did try some pH adjustments, trying either raising or lowering the pH, but again, that didn't really have that much of an effect on the performance of the polymers here. So clearly, relative to the groundwater, we have, as you might expect, some interferences from the constituents that are in the leachate. And so the question really is, well, what is it? The TOC that is interfering? Is it the ionic strength? And we have some tests underway, some differential testing with powdered activated carbon to see, treated with carbon, does it improve the polymer performance? We have some initial data that suggests that perhaps it does. So this may be a TOC effect. So we're working on that to try to see if we can determine what the impact is of the sort of non-ideal nature of the leachate relative to the groundwater. We're also doing some work. Again, we mentioned the daily cover, doing some work with that to see if we can come up with a combination there that can achieve some removal. And if we can get some removal by that method, then once we find a combination that works, then we can look at the leachability question, which is the next part of this in terms of the next steps for the project. And with that, I could take any questions that folks have.
I'm muted again. There's a few that came in, Todd.
Okay.
The one from Kurt Anderson, and this is one I was thinking of, like looking at your concentrations. What essentially percent removal are you getting with the sequestration? And how much are you able to remove, and how much is still left in the liquid phase?
I would say,
and it seems like it varies, right?
It does vary. I would say, you know, I don't have the number in front of mind, but what we've attempted thus far, something less than 10%, I would say, just based on the overall numbers. So not a huge percent removal as of yet. And again, that's largely related to the strength of the TOC, we think, in the leachate that interferes.
Yeah, that's what I was thinking too. It could be the TOC having interferences with absorption sites on the polymer. A question next from Julie Bridgestrup. Julie's a former student of mine who did PFAS work for her master's degree. She asked about the leachate samples that you did use. Were those from closed landfills in Minnesota, closed bay under MPCA regulations, or just all MSW landfills?
They're MSW landfills. These particular ones were active landfills. So no, we didn't collect anything from closed landfills. That would be interesting to see how that compares. In fact, I haven't dug into it to see if we can get our hands on the full data set that the MPCA collected for those closed landfills to see, you know, exactly which PFAS compounds they looked at and how those, you know, compare with what we measured here. That would be a good.
I wonder if there's kind of do two distinct populations or not, whether that's the case. That would be interesting to find out.
Mm-hmm.
Here's one from Kurt Anderson, goes back to that essentially the percent removal is. So it seems like you're still pretty early on in the work, but you have a sense for kind of what kind of dosing you might need to use, and how that might affect how practical it is?
Yeah, it's looking like the dosing is going to have to be quite high. And if you can even, you know, practically get that much into the solution without making sort of a gel like you're referring to earlier. And it may be that you need to do something with the TOC in order to get this to work, you know, at a reasonable dose. You know, that one obvious thing is activated carbon, but that in and of itself can be a treatment for PFAS anyway. Thing that I thought about was integrating this with a biological process where maybe that would consume some of the TOC and reduce that a bit and maybe make the polymer a little more effective. So that's another possible process modification that you could look at here.
So now thinking about your dosages you're using, they're more akin to what you might be using in a wastewater treatment plant for clarification. Is it? I'm used to thinking about polymer gels. So
no, they're higher than that. Yeah, they maybe are more akin to. So if you think of using a polymer in a sludge dewatering application, a little more akin to that in terms of the dose level, which I guess, you know, I wasn't too surprised that it would need to be, you know, quite a bit higher than what's applied in wastewater, because this is a much more concentrated matrix. I would expect you to use a higher dose. And so yes, that's more where I think the dose is probably going to be.
Yeah, that makes sense. Another question from Julie Bridgetup. Are you going to look at other types of polymers, look at different conformations, perhaps different types of polymer chemistry to optimize this?
We don't have any plans to do that. Really, we thought about potentially looking at a more selective polymer chemistry. Really what we were trying to do here, the goal and the spirit of this was to try to work with something that is not a super specialized reagent or you know, a proprietary product. Really, we're trying to stick to that, and you know, I guess either that works or perhaps doesn't. But really, the goal was to try to find something that you know, that wasn't proprietary and wouldn't be difficult to get your hands on or costly to use.
Yeah, a very practical solution in that way.
Right.
Mike Donovan, Mike's a polymer scientist, by the way, so he might ask us some hard questions.
That's good.
Mike just had a question. If you could just repeat the doses you were using, he didn't quite catch that earlier.
Sure. It ranged from 50 milligrams per liter to 1,000.
Great, thanks. Question from Curie Mixon. Do you anticipate that stabilization in solids are reversible? Do you see this as a one-way process, or whether there'll be some mobility later on?
Right. So we haven't been able to test that yet. We got to get it to stick to the solids first in order to test it. So we haven't tested that yet, but in discussing with the professors there, they have said that it's fairly irreversible or fairly stable in terms of the complex that's formed between the polymer and the PFAS compound, at least in the applications where they've applied this and tested it. So in the absence of any other data, that would be my opinion at the moment. But this matrix is very different than what was tested previously. So if you get a major swing in pH or change in ionic strength, something to that effect, you know, that's why we would have to test this.
Yeah, that makes sense. You're kind of in new territory for these surface reactions, right?
Right. Mm-hmm.
Yeah. This is a similar question. This is from Brian Brazil. Do you expect the polymer will denature in the landfill? And mixing it in your treatment vessel, and then you're putting it in the landfill where it's going to be in a really different, potentially different chemistry, right? Different and different physical condition too, in terms of temperature and perhaps redox conditions.
Right.
Do you anticipate that the polymer might just disintegrate?
It might. You know, that's a good point, and that's sort of a long-term. That would be sort of a long-term question, or a more longer-term test would be required for that, because yeah, that tends to be a slower process, the breakdown of the polymer. Certainly under the strongly reducing conditions within the landfill. That's certainly a possibility. Again, not something we've tested yet, but that could occur, yes.
Yeah, I guess you'll find out, right? That's all part of the fun of research, right?
Yeah, exactly. Yep.
Yeah, and a question from Richard Hampel, and this is one that's actually been on my mind as well. Have you looked at any other types of materials that you might use, you know, high volume industrial waste products that you're perhaps going to take as a for a tipping fee that might be a good sorption agent? I keep thinking about, you know, looking at compost, right? I got lots of organic surfaces on there. Could you use something like that and create almost reactive layers in the landfill?
Yeah, we haven't looked at that in much detail. I mean, we thought about the daily cover as something that, that's being handled anyway and put in. But you make a good point. I mean, perhaps there are other types of waste materials that could be looked at as sort of a host for the polymer and the surface for the reaction. Compost is one that's a good idea. Sort of depends on, I guess what it would be sort of a regional thing. What wastes are received in large volume like that could be worked with. So that's a really good idea. We should take a look at that.
We'll put it on your project, right?
Yeah, right, exactly.
A couple other other questions that came in written earlier. Think about the benefits and limitations of what you're doing relative to other technologies like activated carbon ion exchange, some advanced oxidation methods. Can you kind of compare and contrast to? Certainly, this seems like something that's got a lot lower cost and perhaps is a lot more practical if you can get the absorption capacity higher. Some thoughts on that?
Yeah, I think in terms of advantages, most of them, like you're saying, have to do with the cost and the implementability of it. Also in thinking about some of the other technologies, depending on where you're deploying that, you may need to do some pre-treatment for solids anyway. And so this could be a sort of a complementary technology to that in that regard. In terms of limitations, I think it has some of the same limitations that the other technologies do, but perhaps for some parameters, the TOC, you may be just limited in terms of your ability to increase the dose or the ratio of the reagent to the leachate in order to overcome that. Something like activated carbon, you have a lot of absorption sites. You can continue to increase the dose because it's just a physical contact limitation, as opposed to sort of a polymer interaction. So I would say that the limitations are similar, but maybe the levels could be different in terms of the interference from some of the other parameters.
Yeah, that makes sense. The other question that came in written earlier, we've been talking about landfills today. That's what our community's generally interested in. But we get PFAS-laden wastewaters coming into POTWs, right? And into wastewater treatment plants. And could you take this technology and use it as a pre-treatment step at a treatment plant, and perhaps then the solids go back to the landfill with the rest of the solids that are being managed at the facility?
Yeah, and so that's another good point. I think in terms of where the place to deploy this technology could be, one advantage of deploying it at the wastewater plant is now you've got a lower concentration of all the constituents that interfere. On the other hand, you have a lot larger volume to deal with, so that it's kind of a double-edged sword there. But yes, you could look at this, and I do believe the research team at the university, I don't know if they have an actual project on that, but I know that is something that they were looking at as well. Another sort of application of this same approach that they've used in groundwater. Can they use that in the landfill or at the wastewater treatment plant?
Yeah, that makes sense. Yeah, I mean, if you're using it for groundwater applications, you certainly could port it over to a wastewater treatment plant or a landfill, right? Potentially, yeah. The challenge is figuring out the chemistry, right? That's alters your ability to bind the PFAS. Well, we're
Yes.
almost on the hour. Is there anything you would like to close with or to share with the group?
Just that this has been a great opportunity to try to work on this problem. You know, I've learned a lot as a result of it, and I've really enjoyed, you know, interacting with the folks at the university and the folks at EREF and all my colleagues in working on this. You know, we have a few more things left to try on this before we complete the project. So I'm looking forward to that. And, you know, some good ideas were shared here today that I think we can go back and talk with the professors about. So I'm looking forward to doing that as well. Yeah, just happy to have the opportunity to work on this.
Oh, wonderful. This has been really great, Todd. I appreciate you taking the time to share with our community. Remember that if you want to download his slides, they're available in the handout section of the GoToWebinar control panel. And this is one of several science sessions that we're having. And we've got a follow-on to this next Thursday with Mike Wong of Rice University. Here we're talking about sequestration. They'll be talking about destruction. So two different sides of the coin. Probably some combination of all these factors are what we're going to end up doing in practice. So thanks a lot, Todd. And thanks everybody for joining. We're really grateful for everybody's participation.
Thank you. Thanks, everyone.